So today, for week 6 of our workshop, next week is our last week of this 7-week workshop. Our main topic is going to be some statistical values, linear regression, sensitivity analysis. Before we get started on all of that, here's our reminders again. So for the competition, the registration closes February 18th at 4 p.m. Eastern time, which is this Friday. So hopefully you've started building a team. Hopefully you have a teacher that's willing to be an advisor, because that needs to be done this Friday by 4 p.m. And then the actual challenge starts next week. So the next weekend after this weekend, February 25th to the 28th. So just 10 days away to the actual challenge starting. So definitely have those on mind and get registered if you're planning on competing. As always, thank you for all of you for joining and for your participation during these workshops. It really makes it go very smoothly and more enjoyable, I think, for all of us when we get great participation. So thank you to all of you. And then, of course, as with the previous ones, the workshops are being recorded and then they're being uploaded to YouTube within 24 hours after each session. As we go through today, if you have questions, use the Q&A feature. That way it's kind of highlighted, it's spotlighted for our volunteers. And you can also put them in the chat, but the Q&A feature will be easier to answer them. Either a volunteer can answer it immediately or I can answer it once I see it and I'm able to get to it. And then when we ask questions and you respond, you'll respond in the chat, and we encourage you, if you're comfortable, to respond to everybody rather than just to the host and panelists, so that all the other participants can see your answer as well, and we can brainstorm some of these ideas. All right, so this week's leads, of course, I'm running the first hour. My name is Nathan Willis. I'm a PhD student at the University of Utah. And again, this is going to be on mainly like the main topics are linear regression and sensitivity analysis. The second hour is going to be Wesley Hamilton, who's also at the University of Utah. And Wesley will be finishing up on the M3C 2018 problem on food insecurity that Julie started last week, or wasted food and food insecurity. So Wesley will be talking about that, the submission analysis, in the second hour. Our wonderful volunteers, same as always, we have Owen, Julie, Keishav, and Zhao, all of who are associated with the University of Utah. Okay. Let's go ahead and get started talking about mainly linear regression. So when we think about linear regression, some questions that we might ask, just given some data set, is, if we have two variables, x and y, does x cause y? If we think that it does, how strongly can we say that x causes y? And then when we talk about, x causing y, really we're talking about like a relationship between x and y. And, we can look at these things and say, is this relationship look linear, cubic, logarithmic, exponential? Whatever, it doesn't necessarily need to be linear. And we'll talk about when it's not linear, what do you do at the end of this presentation. But first, let's just go through these kind of one at a time and look at this first one about saying, like, does x cause y? So if you think about the way that we have this here with this data set, we have x and f of x. So there's really an independent and dependent variable. In this case, we can really draw that causation between the two. But in practice, when you have a data set, we're going to get to this point a lot in this presentation, that saying that x causes y is a much more difficult thing. So really, when we say does x cause y, we're thinking about like, is there a relationship? And then specifically we want to know, is this relationship linear? Right? So if we plotted this data, instead of just looking at the table on the left, well, we can see that when we plot this data, it looks like there's kind of a line that we could drive through here. Right? So this is what we say when the data, if the relationship is linear, is, maybe you could draw a line through here and you could pretty well approximate all the y values for some given x value by following along that line. All right, so that's what we mean when we say the relationship is linear. And then maybe if you have this relationship, you can think like x causes y, but we're going to really talk about that exact word of what does it mean to cause something in a little bit. All right, with that, can we say like how strongly does x cause y? And again, I'd rather say this in the terms of like how strong is that relationship between x and y, and specifically how strong is that linear relationship between x and y? What does that mean? We'll cover this in just a second. But first, let's think about this thing. Is like x actually causing y, or is there just like some relationship that we're viewing here? And that's going to be kind of a main topic for today, at least for this first half. Okay. So here's some examples. This first one is from miasma theory. Right. So if we look at this diagram here, we can think of like some bad germs, and those bad germs can maybe cause like rotting flesh or something, and that could lead to bad smells. Right. Bad germs can also cause disease. And so miasma theory, which essentially says like bad air, says that bad air causes disease. And this was a common belief with like cholera or the Black Plague in earlier times. right? So they thought like just the bad smells cause disease because they saw that as the bad smells went up, the disease went up, right? And so you can see here that there's definitely a correlation that when one goes up, the other goes up, but there's not causation, right? The thing that's causing the germs or the thing that's causing the bad smells and the disease is the germs, but there has to be a correlation. So again, there's definitely a correlation between these values, but there's not causation. All right. Another one from some historical data is, the rise of the polio in the 1950s. Right. So again, it heats up in the summer, and polio had this phenomenon that it's really like a summer disease. We think about the common flu these days as being like a fall and winter illness that goes up every fall and winter. Well, polio would go up during the summers, right? So we can see on this plot up in the top right that whenever, ice cream sales went up, the cases of polio went up. Whenever ice cream sales went down, the cases of polio went down. So they're very following the exact same pattern. And so again, you could look at this plot and say, oh, like ice cream sales or kids eating ice cream is what's causing polio, because there's definitely a correlation there. But the underlying, there's just a correlation, it's not causation, right? So this just happens to be the summer heat. Of course, when it gets hot, kids buy more ice cream. And when it gets hot, that increases the cases of polio. So again, there would be a clear correlation looking at this plot. They really go hand in hand with one another, but there's not causation. Kids eating ice cream is not causing polio. And this is, again, something that was considered in the 50s or in the late 40s, early 50s when they were having all these rising cases of polio. Yeah. So the last example here, and this comes from a website called tylervegan.com. And this last example is a bit morbid, but it kind of, I think, gets this idea of how much you can look at correlation and get to some pretty radical ideas, right? So here on this left axis is per capita cheese consumption, and on the right axis is number of people who died by becoming tangled in their bag cheese. And you can see that this really goes up exactly together. And the correlation of this data set is 94%, right? And so there's a very strong correlation between the two data sets, but I don't think anybody's going to claim that the overall cheese consumption increases the number of people who happen to die in their bed cheese. Right, so there's maybe some underlying thing here. These are probably like completely independent, I would say, or they could just be going up with the population because these aren't being scaled by population. These aren't relative numbers. But yeah, so here's 3 different slides, all of which is getting to the same idea that correlation is not causation. So when we say, does X cause Y, this is a very difficult question to answer. I'll say that it's kind of outside the scope of this presentation. If you wanted to do these things, I think the main idea is like to get the hypothesis testing. You create a hypothesis, and then you test that in different ways. There's really sophisticated statistical tools to do this, like chi-square test, or you could, of course, go like an experimental route. Like you need to do experiments to test if this is happening and remove X and see if Y still happens. So again, that's outside the scope of this presentation. If you want to get causation, that's a much harder thing to do. And so just make sure when you're actually submitting your M3C reports, you don't claim to be causing that. What you're doing is saying one thing causes another, unless you've like really been able to test that out in some other way. Because just what we're looking at here with linear regression or these statistical tools don't necessarily tell you causation. It's a very difficult question to answer. Okay. Right. So with that kind of warning going into this about correlation versus causation, let's see like what can we actually do with these statistical ideas. All right, so the main idea for all of this presentation today is we have some data and we want to create some model. And I think maybe it's easier to think about this as like data minus model. What's the difference between your data and your model? Well, that's an error, right? So here we can think about this in terms of data is the model plus whatever error, whatever thing we can't account for in our model, right? Because of course, data is a very difficult, it's observed in the real world, it's very complicated. Our models, we generally want to be somewhat simplistic in some sense, such that it's understandable. We want to be sophisticated enough to capture whatever phenomenon we're trying to, but simple enough that's understandable. And so, of course, there's going to be some error in any model. There's going to be some error. Right? So what's one of the more simple models to come up with, but still a very powerful one that I think gets used a lot, is a linear model. And this is why it's nice to think about that in terms of data equals model plus error. Because here we can say that Y could be like the understanding of the data, BX could be the model, which is just a line, and then E is the error or the noise, right? So here's a really nice way to think about exactly our model in terms of our data and our error all in one slide. Okay, so with this, right, what are we saying? We're saying that we think that our data fits some linear relationship, and we want to figure out what is this B or the slope that we can just approximate all of our data off of that. I will say that this is actually a simplified linear model. There is like a built-in assumption here. So just by looking at this and thinking about a general equation of a line, can anybody tell me like what the built-in assumption is here? So maybe I'll give you about 30 seconds. Put it in the chat if you know. This is already simplified. So what is the built-in assumption on this model? Any ideas? So again, we have an equation of a line here where it's bx plus e, but e is the error, and we have some built-in assumption. All right, so I'll just go ahead and give it away. But the built-in assumption is that we're assuming this has zero slope. So we're assuming this is a linear model. Absolutely, that's a great point. And then we're assuming that they're directly correlated. It's very good. Thank you. Sorry, I guess I just didn't give you enough time. Now they're kind of rolling in. Thank you for your answers. One thing that we are definitely assuming on top of both of those things is that the slope intercept is zero, right? If we think about any line in slope intercept form, it's mx plus b, right? Or the slope times x plus the y-intercept. But here, if our model is b times x, and we're saying that e is the error, that's not a part of our model, that's just the error that would come out of it. Well, we're saying that the slope intercept is zero. Yeah, so that is a simplifying assumption to make this an even simpler model. And the reason why is so that when we write this down on the next slide, it's just a little bit more simple. But maybe this would be a good idea, depending on what data set you're looking at. So can you think of any two data sets, some x and y, that are linear related and they have a nice linear correlation, where the y-intercept would be zero? And what would that mean in terms of the data? So again, I'll give you maybe a minute, because I don't think 30 seconds is quite enough time to get your answers typed up. But think of some linear relation where if one of the things is zero, the other is zero. So what kind of data, just any data you can think of that would be true for? So again, the question is, in this model, the way that we've written it, it's a simplified linear model because it's assuming the y-intercept is zero. And then can you just think of some example of data that you could be given or that you could measure where a slope intercept of zero is a good thing to assume from the beginning rather than solving for it later? Okay, great. So here's some examples. If you have a dead phone, then 0 minutes charging gives 0% charge, right? And then the other one is if you're keeping track of how much food you've eaten in a week, if you start at the beginning of the week, 0 pounds. So at time 0, you have 0 pounds. The amount of money gained based off the number of sales, right? Yep, 0, 0, person's age. Yes, these are all great examples. So this is a simplifying assumption. Maybe you want to do this from the beginning, but it's not the most general linear model we come up with, and we'll look at that later. One that I thought of would be like height and weight, right? Of course, if your height is 0, your weight is going to be 0. And another one that we heard previously from somebody else was the number of words you know versus your age, right? So when you're age 0, when you're just born, you don't know any words. And so it makes sense to be 0, 0. I think that one is really good for the slope intercept, but it may not be linear, right? You think, well, when you're young, you don't learn words for about 18 months, and then you start to learn a few words, then you learn a lot of words, and then you start learning less and less words as you get older. So again, that would really fit the y-intercept idea, but maybe not the linear idea. Okay, so kind of with this idea of data, model, assumptions, error, let's go ahead and actually look at how do we do this, right? How do we actually find this value of b? Right, so here's the same plot that we had before. And the way that we do this is we're going to think about some line that we draw through our data. Each of these gray dots is our measured value. This is the data we were given. And this red line, if we pick an x value, we go to the red line, we'll get some y value. We're saying that this is our predicted value. right? And then the difference between these two is called the residual, right? So for every data value, you would get a residual. We square all these so that they're all positive, and then we add them up, right? And you think that the line of best fit, or the one line that we're looking for, is going to minimize that residual sum of the squares, which is right here in white. And so that's the overall goal of how we find B. The actual value of B is given here, where this capital sigma, right, sub I, means that you're summing over all the indices I. And so you take yi times xi, right? So this would be y1 times x1 plus y2 times x2 up to yn times xn, and then divided by xi squared for each of those summed up. Okay. If you want to actually work out what this value of b is, you can look at this equation here. And if you know calculus, this is really just a minimization problem with respect to the variable b, and you can work out what this is for yourself. All right, for here, we're just going to go ahead and give it to you. And let's look at our first example. Right. So here again is assuming that the slope intercept is 0. And so I'm going to pick an example that kind of fits with that idea. Okay, so hopefully we can all see the MATLAB live code. All right, this first one is, we're just going to read in some fish data, right? So this is from Kaggle, and it's fish.csv. Again, it needs to be in your working directory if you're trying to follow along. So make sure it's in your current folder. And this read table just reads in and saves as a table. This next line, when it reads it in, all these species are saved as strings. So we're just going to change it to categorical for MATLAB purposes. So that part, I'm going to run that, right? I would always recommend viewing your data set, like actually look at the data set, get an understanding of what we're looking at. Let me run this cell. Good. All right, so we see here that this data set is 159 rows by 7 columns. The columns are species, weight, 3 different lengths, which I think are like different fin lengths and overall lengths, and the height and the width, right? So again, just look through it. We see that the first many species are all bream, and then a lot of them are roach. Okay? So now that's viewing the data, so let's actually visualize it. So let's say that we want to figure out some relation between the width of the fish and the height of the fish. Again, I think this makes sense that this stuff is a y-intercept of 0, so we're just going to go with our built-in model. Okay? And then we're going to put them on a scatter plot, and the rest of this is all just to make our plot look a little bit more nice. Okay. So this first line here, sorry, this goes to the fish data set and it grabs the width column, and we saved it as a vector x. Then we did the same thing with the height column, we saved it as a vector y. Okay. And here's the data, right? So you can see that it certainly looks like there's a nice linear relationship here, but it looks like it's kind of, I guess, like bisected into 2 different groups. Okay, so are there any ideas on like why we see 2 different distinct groups here? Any thoughts about why it looks like there's 2 different groups here? They both look linear, but it clearly looks like we have 2 different groups. Any thoughts? Yeah, perfect. So thank you. The first 2 answers say that there's 2 different species. That's the first thing I would have thought of. The third one makes a lot of sense that I didn't even think about. It could be like male and female. Maybe we haven't accounted for the sex of the fish, and so maybe it's a male and female difference. So that's a great point as well. I would say if you see this on the actual model, you should dig into your data set a little bit more. So for this one, let's see what happens. There's this function called gscatter, which is like a group scatter plot. I have to get rid of the line width because it'll get mad. And what does gscatter take in? Well, it takes an x, y, and group. And we're going to group these by species. We don't have a label for sex, so we can't actually check that in this case. But if you had the sex of each fish that was measured, you could go ahead and test that as well. So let's do fish.species and run it again. There we go. Right, we see very clearly now that if the colors are coming through clearly on the zoom, you know, the bream and the parky are the yellow and the red, and that's this first group. And then the other 5 fish make up this group here. So again, if this was actually something that you saw in the model for your problem, maybe you want to split your model, your linear model, into 2 different groups. You know, model the bream and parky as one group, And the perch, pike, roach, smelt, and whitefish is a separate group. And this would be something that you'd build into your assumptions of your solution. And your justification could be this plot. Like we can clearly see that there's two different groups. And so we're going to model each of them with their own linear model. Okay, great. Thank you again for your answers. Let's go ahead and actually find the value of B and see what that plot looks like. Okay. So remember, what was B? It was the sum of x times y for every single value that we have for every single data point. So x is our width and y is our height. Okay. And remember, this dot times just does an element y. So these are vectors. And it just says, takes the first element of x, multiplied by the first element of y, second element of x, second element of y, so on and so forth. And then we add all those up. So that's exactly that sum of x times y. And then the same thing for the denominator. So this is going to give us that value of b that we had before. And then I'm just going to plot it, x. And now instead of plotting x times y, we're going to plot the data, right? The model, b times x. Okay. Okay, great. And now we can see here that this line goes through here. And it does a pretty good job. Again, you can think if we separated out these two groups, you'd get a much better fit for each model. But we could see some idea of our, kind of our introductory model here by keeping it all as one group. So we're not going to take the time to, break apart these two groups right now, but that can give you some idea of what you could do. Okay, great. So let's go ahead. Now that we know how to find a line, and again, you can also include a y-intercept. So instead of just like b times x, you can do mx plus b. And you can find m very similarly, but we're going to see later that there are just built-in functions in MATLAB that do this for us. So we don't really need to do this by hand every time. Yeah. So with that, let's go ahead and just think about, now that we have some solution, right? How do we measure how good it is, right? So we know that this line was made to minimize all the residuals. But what does that mean in terms of our actual data set? And the way that we really want to think about this is like the noise of the data set. Like how much of the noise are we capturing or are we understanding? Right, so if you have a very noisy data set, it's going to be very difficult. If you have a data set that has no noise, and remember here we're thinking about our data has a linear relation. So no noise means it fits exactly onto a line. Well, in that case, then every residual would be 0. Okay? But we also want to incorporate like the relative size of the problem here. And the example that we have here is, if we're measuring distance between planets and you have a few hundred miles, this is very, very small, right? When you divide by the overall distance between the planets. But if you're measuring in between cities, this is massive, right? So we want to really get this idea of relativeness into our idea of like how good our line is. Okay? So keeping that in mind, let's go ahead and like look at the actual values of what we do. All right, so like I said, we kind of talk about the noise, or let's make it more clear and say the variation. And with this, we're going to use this r squared value. All right, so the r squared value is going to tell us this number between 0 and 1, and it tells us how much variation is explained by our linear model. Okay. So first, to do this, we want to figure out what is the average of all the observations. All right, this is adding them all up and dividing by the total number. And this is marked by this purple line here. And this is at exactly 7.25. If you go back to that first slide that had the numbers, you can see that the average of all 8 numbers is 7.25. Okay. And then the variance, well, the variance is looking between the mean or the average and the predicted or the measured value for each of them, right? So here it's very, very small. Over here it's quite big again. And to get the overall variance, we square that value. So you can think about the length of these green bars, you square all of them and you add them up. And so this kind of tells us how much each value is moving away from the mean or the overall variance of the data set. And to get the r squared value, right, we want to think, how much of this variance is our model capturing? So I think this is easy if we look at this example right here, right? And we think about the residual. So remember, the residual is going to be the distance between this gray dot and the red line. Right? And so we've captured that much of that green bar, and then we'd have all of this left that's not captured, right? And so we can, so the difference between this purple line and the red line is how much of the variance we did capture. And then the distance between the red line and the gray dot is how much we didn't capture. So really, the residual sum of the squares, something we've already talked about, is the amount of the variance that you're not capturing with your data set, right? So that's the overall amount. And so we want to get this between 0 and 1. So what we do is we divide by the total variance. That's again all the green bars. And this is going to give us a percent of the variance that's not captured by our line. Okay? So this is SS res divided by SS total is the percent of how much we're not capturing, right? Some number between 0 and 1. And so of course we want the amount that we are capturing. We take 1 minus that value. And this is R squared. So again, if there's absolutely no noise, we'd have no residuals. Those would all be 0. And SS res would be 0 and R squared would be 1. So an R squared of 1 tells you you've captured all of the variance in your problem, right? You've hit it exactly. An R squared close to 0 means you haven't captured a lot of the variance, and your predictions aren't going to be nearly as tight as you would maybe want from your model. All right, so here's really that same idea I just said. Sorry. All right, so if SS res is 0, that means R squared is 1. Alternatively, if you have nothing but 100% noise around the mean, you're really going to get back you're going to get your mean back as your line. And in this case, SS total and SS res are equal to each other. So that fraction would be 1, and you get R squared is 0. So the main takeaway here is R squared value goes between 0 and 1, and a value closer to 1 means you're capturing more variance of the data set with your line. All right, so with these two examples here, we have an R squared value of 0.81, and we see that those dots are very tightly fit around our line. So you can think like another way to think of this R squared is how tight your data fits to your line. And the R squared value of 0.24 is very widely spread out around the line. Okay. Right, so if you measured this at some point on the x-axis and got back the y value, you would expect the true value, right, to be somewhere around that data set. Where in this one, you wouldn't have nearly as much, as strong of an idea of how tightly that would be around if you use that to predict some value. Okay, another example, just putting those kind of two ideas on the same plot is right here, where if you have two R squared values of 0.985 and 0.881, hopefully the two different shadings are coming through on Zoom. Excuse me. Right, so again, the 0.985, these values are very close to the line. So if you wanted to, think about y, so now the horizontal axis is y at 20, and you get a prediction of 20, because all of your data is very tightly around that line, you'd say this is probably a pretty good idea of what the true value would be at that y equals 20. Where with the 0.881, it's still a pretty good fit. We can really see the difference between the two, tightness or fit around the line. It's just not as tight as the 0.985. If you are familiar with the idea of correlation, correlation is a value ranging between -1 and 1. And the R squared value is just the square of the correlation. So this just puts it between 0 and 1. And it has some nice properties aside from that, but we're not really going to talk about those details right now. Just keep an idea, if you're comfortable with correlation, this is just the square of that value. And this is the R squared number. So this really kind of takes us back to our original question of like how strong is the relationship between X and Y. So if the R squared value is very close to 1, we can say this linear relationship is very strong. Where if it's small, it's not as strong. Okay. Right. So before going on and talking about like what do we do if the data is not linear, hopefully we have a good idea, a good starting point of how to handle linear data and model that with a line of best fit. Before going on to nonlinear data, what if you only look at this data and not actually visualizing it? So here's, it's called Anscombe's quartet. It's this famous example of these 4 different data sets. We can visually look at these and say that these are behaving very differently, but they each have the exact same mean and variance for the X values. And they have nearly the same, I think to like 2 or 3 decimal places, mean and variance for the Y values, line of best fit, correlation, and R squared, right? So if you just looked at the statistical values, right? So if you just took your data set and said, I want the mean and variance of each direction and calculate a line of best fit, these are all going to give you the exact same numerical value, even though we can look at them and say they're very different, right? This one actually looks like it's probably a pretty good model to be done linearly. This is most likely a parabola, right? If we look at that, you should probably be fitting that with a parabola and not a line. This is actually, pretty linear, except for this one right here. So here you're just never going to capture this outlier, right? And of course, this outlier is also changing the slope between these two data sets. Okay? And then here we saw a bunch of values grouped together. So the line's probably not doing a great job either. It looks like there was a question or somebody raise their hand, if you have a question, want to put it in the chat or the Q&A, go ahead and do that. Okay. Yeah, so if you do have a question, go ahead and put it in the Q&A. We'll keep an eye out for that. I'm not sure if the hand raise was a mistake, but I'll keep an eye for that. Okay, so what's the takeaway of this? Again, you have these statistical values. They are very important. They can give you a lot of information. But I would just say always visualize your data. Right? So you really want to take all of this together as a whole. You don't want to be picking and choosing just the mean or the variance without looking at the data, because each of these will give you the same mean and variance, but we can tell they're behaving very differently. You're going to want to handle them differently with your model, right? So we looked at the fish data and we looked at the actual data set and then we plotted it and then we drew a line. So again, you want to do all of this together and get back to the actual, make sure you're answering the question and you have a good assumption using a linear model before just like diving into the numbers. Okay, so hopefully we have a good idea of linear regression. We have some warnings about correlation versus causation. We have some warnings with Anscombe's quartet, and some always visualize, this idea of always visualizing your data. Let's wrap up this first half before going into sensitivity analysis and talking about like, what do you do if your data is nonlinear, right? So if you plot your data and you say, this doesn't look linear to me, I don't really want to fit this linear model. What can be done? Do you just give up, or are there other things to do, right? Of course, we're probably going to be saying this if you just give up. So what can we do? Well, the idea is that you're going to map it onto a different variable. You're going to use some function that maps it to a new variable and do linear regression on that variable. So we're going to look at this example in a second. This is from some car data where you have the price of the car on the horizontal axis and the miles per gallon on the y-axis. And you could think you could fit a line through here, but maybe it's not going to give you the best model. So what can we do? Right. And again, we're going to map this to a new variable that hopefully has a better linear relationship. There are multiple mappings you can do, but I'd say the most common one is you're going to take the log of each value. So let's just go ahead and come back over here to our MATLAB live script and try this example. So again, we're just going to read in the data, change things to categorical rather than strings. Let's view our data. And so we have, right, it's 153 rows with 9 columns. Those columns are the car ID, the kind of vehicle, that's like the name we would say we'd see on the side of the car, the year. The MSRP is manufacturer suggested retail price, right? That's what we're actually going to want because we're comparing car price to miles per gallon. The accelerate, not sure exactly what this is. And then there's some other IDs over here. But again, if you think about what we just looked at, we're interested in the car price versus the miles per gallon. And so we really want this column here and this column here. So you can go and look at what these are later, but we don't need what these actual values are over here. Okay. So again, the idea that we're trying to get at here is say that we want to know if more expensive hybrids, because all the cars in data set are hybrid, have better gas mileage. Okay. So the first thing we want to do is grab the MSRP, manufacturer's just retail price, and the miles per gallon columns and save them as vectors. Very similar to what we did before. And let's plot a scatter plot. Okay. Okay, and again, these last few lines here are just details to make the plot have larger values and easier to read. Okay, so again, this is the exact same data plot that we saw before on that last slide. And now, how do we actually transform the data? Well, again, this doesn't look that linear, and so we're going to log transform the data. So we're going to take the log of each data, of each set of data, and we're going to save those as new variables. So here we have x log is log of x, y log is y log of y. And now let's plot this. All right, here's the new data set. And if you draw a line through the middle of this, things seem to be a little bit more evenly spread out around that line than they were before. Right. So again, of course, you can draw a line through this data. It just maybe doesn't approximate all the data that well. And we'll compare the two data sets and the lines at the end after we make our model. Okay. But the reason for why we use logs is because the nice properties the logarithms have. We're not going to go into those details here, but if you write out the log on the line, it gives you back a power function, right? So if you think that your data has some like power relation, so x to the m, then log fitting your data will give you something back that looks linear, and you can figure out from the slope of that linear relationship what is the power. Okay, so that's kind of beyond the overall idea here. Okay, so like I said, we're going to use a built-in MATLAB function to do this. So in this case, we're not assuming that the y-intercept is 0 anymore, because we're not actually writing down the b value by hand. We're just going to compute it out with MATLAB. And so this fit linear model between the x log and the y log. Okay? And we're going to save that into model. And maybe let's just look at what this model looks like. Okay, right. So here's what model gives us. Like this is what fit LM gives us back, and it's you can see it's saved in the variable model, and it gives us all this information here. Right. It gives us the estimates for our intercept and our x1. So these are the mx, the m, and the b in our mx plus b line. Right. You can see it says it's like a constant plus x1. And then this is the standard error for these values, the t-stat and the p-values. These are more sophisticated statistical things to look at. We're not going to focus on right now. But really, we want these two things. And we can also see that we get our r-squared value. You get a root mean squared error. You get an adjusted r-squared. So what do we want out of this? We want to go into the model and we want to find the coefficients, right? You can see that this is saved as coefficients. And then we want the estimate column of the coefficients. So that's this model.coefficients.estimate, right? And now we want to save the first one as intercept. And the second one looks like this got pushed into the last line. There we go. Right, we're going to save the first one as intercept and the second one as slope, right? So the b is going to be the y-intercept, and then x1 gives you back the slope of your line. Okay. I'm just printing them out here in plain text so they're easier to read. So our model would be that y is equal to minus 0.3732 x plus 7.402. Okay, all right, and now we can actually look at this plot here. All right, so we have this line that's plotted through our data here. Again, it doesn't look like it's fit that tightly around it, but we can, of course, quantify that with our r-squared value, which we have right here. So let's look at that, and then we'll look at the untransformed data. So the r-squared value is 0.332. So we say that we've captured 33% of the overall variance in the log transformed data set. All right, so maybe this isn't great, but we'll see in a second why this might be a better idea than doing it on the untransformed data set. Right. So this isn't car price in miles per gallon on the x and y axis. It's the log of those variables. Okay. So let's go back to the original data set. So we'll take the exponential of both sides essentially. Right. So the exponential of the log of x is just going to give us back x. Right. And then here, remember, our model is mx plus b, but x is the log of the data set. And then we took the exponential of that. Okay, so let's plot what this looks like in the untransformed data set. Right, so now that line gets mapped to this rational function here. All right, so again, we said that this captures, our linear model in the transformed data set captures 33% of our data. Right, but I think this gives us a more understandable model. Right, if we look at this kind of makes sense. As you increase car price, the miles per gallon can only go so low. Right, it shouldn't be negative. If we just drew a line through this, that would eventually give you negative value. So for a rich enough car, for an expensive enough car, excuse me, you'd get negative miles per gallon. I don't even know how to interpret that, right? That doesn't make much sense. Now, maybe you build into your model and say, we're only going to this car price. You set the domain to your car price so that you don't have to deal with this, or you can do something like this, right? But again, this is how you can deal with nonlinear data. And now you get back this nonlinear function, even though you use the linear analysis to get there. Okay, so with that idea in mind, we're talking about versus a linear model. How would we have done if we had just worked with the untransformed? So here we're going to do the linear model on just x and y. Everything else is pretty much the same, right? And let's see how this does. Right, so here's the model, right? So now remember we had before like 0.3, minus 0.3 for the slope, but that was in the transformed data. Now the slope is minus 0.003 times x. And here's what it looks like. Okay. And then down here is exactly what we want to get to, is like, what is the R squared on this original model? So the R squared value is only 28 or 0.28. So we're only capturing 28%. So the other model doesn't capture that much more variance, right? The transform data, but I think it gives us something that's more understandable, right? It's easier to make sense of what these things actually mean, and it's more realistic. And then it also does give us a little bit higher R squared value, but you could argue that maybe the understandability is the higher thing. Okay, yeah, so this is kind of the end of the linear regression part, right? Again, these last two examples, we're dealing with things that give you nonlinear outputs, but you do a linear analysis to do this. So it's fairly powerful once you get into this idea of like log transforming or transforming with another function to get there. We're going to go into sensitivity analysis. Before that, Wesley put this in the chat, but I'll also add it. If you do have questions, please use the Q&A feature. It's right next to the raise hand button. So if you have questions, please go and just put it in the Q&A and we'll answer it the best that we can. Were there any questions on the linear regression or any of the statistical things that we talked about, like mean and variance, from the previous section before wrapping up with sensitivity analysis? Okay. So if you do have questions, you're always welcome to ask later. Otherwise, let's go ahead and continue on with sensitivity analysis. So why are we kind of grouping these two topics together? Well, I think both of these things really help us get an idea of like how good our model is doing, or what are the limitations of our model. All right. So when we talk about sensitivity analysis, what we're really getting at is like how sensitive is your model to the parameters of your model, right? So if you have a small parameter change, do you have a small output, a small change in your output, or do you have a large output change in your output? And the reason why I think this is really important is we know that we can't necessarily get these parameters 100%. We can get our best guess for the parameters, and you want to be able to say to the judges when you're submitting these things is, okay, we know that our model is not perfect, but if we're wrong by this much on our parameters, this is how much we're going to be wrong by in the output of the model. So that's kind of the main idea of this section. Okay. And I think this is something we kind of got at the last idea in the last section, but really summarized nicely here. Right. All of our models are going to be wrong in some sense. You know, you can build a model on the data you have now, and in a week, if you have new data, you can measure, and you're not going to get everything exactly correct. And so I think this sentence here to summarize this perfectly is all models are wrong, but some are useful. So let's kind of keep that idea in mind as we move forward. And this is true for any level of math model. This is always going to be true. So to demonstrate this, let's look back at our SIR model that I think Keshav introduced a long time ago. And then Julie worked with again 2 weeks ago. We talked about difference and differential equations. All right, so to summarize the SIR model, we have these different parameters or inputs, which is the initial susceptible, infected, or recovered population. Remember, sorry, the SIR model models disease spread for susceptible, infected, and recovered populations. And then we also have the infection rate and the recovery rate. Right? And then the models say that the susceptible population at the next time step is the susceptible population at this time step minus the people that get infected. Right? And that depends on some infection rate and the interaction between susceptible and infected people. All right, the infected population is the current infected population plus the people that got infected minus the people that got recovered, right? And that recovery rate is B. And then we know that all the people in the population stay the same, so we can just model R of T with this last equation. Okay. Okay. So what are we going to do? We're going to start off with these values, and we're going to change them and see what does this do to the overall model. There's the takeaway. Let's actually look at how we make those plots, though. Excuse me. All right. So we're going to just plot each of these things. So I have this SIR model here written as just a script, not a MATLAB Live. All right. That this is exactly the equations we saw before. And we're going to use this with ODE 45 to solve our differential equation for some time stepping. Our initial population Our initial susceptible infected recovery populations are here. We store those as a vector. And now what we want to do is we're going to make a whole bunch of recovery rates. We're going to specifically make 50 of them between 0 and 0.5. We're going to pick a few different, infected rates. We're going to pick a few different recovery rates. And we're going to see how do these values change the overall solution. Okay, and then we're going to look at the recovered population at day 60. So we're going to stop at time 60. And this is just initializing a matrix or a solution array to store our solutions in. So we're going to run this through a loop of each case of B, of each instance of the recovery rate, and each instance of the infection rate. And we're going to store this in recovery. Okay. And then we're going to plot it out. So let's go ahead and run all of this and see what our plot looks like. All right, so here's the exact plot that I saw before that we had on the last slide. All right, so as we increase infection rate, that's happening on the horizontal axis. And we're checking what happens to the 60-day recovered population on the vertical axis. And then we're also just testing this for a few different values of recovery rates. Okay. So we can see that as we increase the infection rate, the 60-day recovered population actually increases. So the population that's recovered by day 60 increases. And I think this might be a little bit counterintuitive to think about at first, but it makes sense when you realize before somebody can be recovered, they have to become infected. And so increasing the infection rate means more people get infected quicker. And so then they can be recovered earlier in the time series. All right, and then we can also check the recovery rate. So as you increase the recovery rate, well, it starts off down here. And now the red line and the yellow line. So as you increase the recovery rate, you get more recovered people at day 60. But you can see that it actually goes back down, right? And I think this has become they're recovering so quickly that the infected population stays lower. And then you can't infect as many people. So not as many people get sick in these cases here. So of course you can't get as many people recovered. So I think these plots are very useful to kind of get an intuitive understanding of what your different values do to your model. And you can really use these to understand like what do these different numbers mean and how does that change what happens in your simulation. All right. The other one that we have here is just going to be flipping these two values. Right. So now we're going to be testing in recovery rate here and infection rate here. Okay. And we have a very similar story. Okay. Where you can just check what happens here. So if I increase the recovery rate, what happens to the 60-day recovered population? Well, initially it goes up, but then it goes back down. I think this is what we just said, that you're recovering so quickly that the infected population doesn't get large enough to make more people sick in that amount of time. And we just take up different values. Yeah. So like I said, I think these plots are really powerful for an intuitive understanding. But if you actually want to put something in your model, you probably want some quantitative thing. I would recommend, of course, putting these plots into your solution, but you also want some quantitative thing, right? So how do we quantitate what we mean by our sensitivity? Well, again, we're just going to think about measuring, what's the difference between these outputs, between these different cases, and then let's scale it to be relative to the problem. So very similar to what we saw in the last one is our absolute error, is our approximation versus minus our observation. In this case, I would say that our observation is going to be, the first value of the recovery rate, and then the approximation is the next value. And what's the difference between those two? Gives us some idea of how this changes. This small change in our input changes the output, right? And then we can scale this by the original value, and of course, multiply by 100 to get to 1%. Okay. So let's do this over here. Right, here's our same example, same initial populations. Now we're just going to test two different A's. So I have that A is 0.2 and A is 0.2 times 1.05. So I'm increasing the infection rate by 5%. And we want to say, what does this do to our model, right? So we're going to test two different things. We're going to test the max infected population over 100 days. So what was the most people that are ever infected at one time? And the 60-day recovered population. If we increase the recovery rate by 5%, not 10%, that's 10%. And very similar, except now we're storing these both at the same time. So I get my solution vector, I go to time 60, and I go to 3 because that's the recovered population. I save it here. And I go to location 2 of all times, and I take the maximum, and that's the maximum over the time. All right. Okay. So again, we're just going to print these to the screen, kind of in plain text. Need to run this cell first, excuse me. It's going to run. There we go. All right? So with the original maximum infection level with A is equal to 0.2, we would have that 41.6% of the population is infected at one time, right? That's the maximum amount that are ever infected at one time, given this initial population of this B. If we increase that 5%, we see that this goes up to 43.2, right? And that would take the difference of these two numbers, and that gives us this absolute error that we talked about, right? So we have max I at 2, max I at 1. And this is about 0.016. Again, let's scale it. So we're on the appropriate scale of our problem. We're going to scale it by the original value. And this is 0.039, and then multiply by 100. So I think this last value is easy to talk about, so that's why we'll do this quickly. Right, so 3.9%. So if we increase the infection rate by 5%, we increase the maximum infected population by about 4%. Right, so this gives you a really good understanding of like, how does our model change? How does some error in our input change the output necessarily? Because you again don't know that A exactly. And then if we just look at the 60-day recovery level, so again the 60-day recovery level is 0.80. If we increase that infection rate 5%, the 60-day recovery, so that's the population that's recovered at day 60, goes up to 81.8. So again, we increased the infection rate and we got a higher population because people became infected more quickly, so they're able to recover earlier on. The difference there is 0.016. We scale that again by this first value and we get 0.02. So that says that the 60-day recovery, that should be 60-day recovery, not maximum infection level, is 2%. So if you increase your infection rate by 5%, your 60-day recovery increases by 2%. Okay. So that was something that could be put into your report that really it shows that you understand the limitations of your model, and you're testing different cases fairly easily and showing what happens if you get an error in one of these inputs. Okay. Of course, we're just doing this with A and B. For this example, you could also do initial population, see how does if the initial population that we thought we had was wrong by 2%, what does this change in the overall model? This other one here, you could also do for the recovery rate, but we'll leave that for you to do on your own. Right. This last part here is just an example of one of the COMAP solutions that actually did a sensitivity analysis on one of these problems. So I'll read this problem. Right. This is from a COMAP, I think high MCM problem about free charging for different things in our society. Right. So in our school and social lives, we exist in the mobile electronic world. Each day we plug in and charge our electronic devices and equipment. These electronics may range from small items, such as cell phones, to large items, such as electric vehicles. While in our own home, our family is most likely responsible for purchasing the charging equipment and then paying an electric company to provide the electricity. Public places are continually expanding the availability of electrical outlets, charging stations, and even electric vehicle charging parking spots. For example, many airports have recently refurbished their parking lots, terminals, and aircraft to allow for electrical charging of everything from portable devices to vehicles. In some locations, these charging ports require a fee, but many public places worldwide offer charging for free. But what is the impact of plugging in our electronics at these free charging sites in public places such as airports, railways, terminals, schools, libraries, shopping malls, coffee shops, and offices, and who paid for it? Right, so that's the prompt. And what this team did is they first, let's just first understand what the model is they took the total cost and they broke it up into total fixed cost and total variable cost. And they said that their fixed cost is the cost of each plug, or I think that could be like a charging station or an outlet. And then how many plugs you put in a year, how many of these charging stations you put in a year. Excuse me. Right, and then the variable cost is the cost of electricity and the cost of how much electricity is used, sorry. So that is their model. And then for their sensitivity analysis, what they do is they say that they can only change the number of EV charging stations or in plug. If we adjust the change in number of charging stations by 5%, here's what happens. So they have this nice table that summarizes the result. We can't look at their entire solution right now. So there are a few things to notice here. But they say that if they change their charging stations by 5%, something goes up by 115,000 in 2019, and something goes up by 139,000. I don't know if they mean total fixed costs or total costs here. But again, these are just snippets taken out of the report, so we're not going to judge them too harshly for that. The other thing I would say here is they say they can only change these things. I don't know why they're claiming they can only change and plug. It's their model. They could also build in and say, what if the cost of electricity varies between this range? What's the total cost at the end? Okay, so that's just one example. And again, I think the sensitivity analysis does a really good job of showing the judges that you understand the limitations of your model and also just testing out what it can do.
So these slides you've seen previously, okay, or this slide you've seen previously, and all of these slides have been moved into the student share folder, so you can access them, okay. The scoring guide that M3C uses can be found here, where it talks a bit about, you know, what teams really should be doing and like keeping in mind as they write up kind of their submissions. In particular, right, define all of your variables and parameters, keep in mind units, justify any assumptions that you're making, clearly describe the mathematical approaches you're using, apply to or demonstrate for any situations presented. And so, right, make sure that you're actually addressing the portions that these, the things that these problems are asking about. And then of course, you know, discuss implications, okay? And then, you know, they give roughly the percentages for, you know, how each portion of your submission is scored. So the executive summary, which is usually like this 1-page overview of everything, right? It's about a fifth of your points. Question 1, it's about 1/5 through the points. Question 2 is about 1/4 of the points. Question 3 is about 15%. But of course, in your actual submission, right, any connections that you can make between all 3 of these questions, you know, they will get you extra, I say, like brownie points. Okay? But anyway, so, you know, as you're preparing your submissions, as you're getting ready to compete, do take a look at the scoring guide. It gives you a sense of, right, what the judges are actually looking for. And so that way you can tailor your submission to, you know, what the judges are looking for. Okay. So then let's go back here. Okay. And so, of course, some other, you know, general guidelines, you know, make everything easy to follow, easy to find, easy to read, and the judges will be overall happier with your submission. Okay, so then, cool, right? So, as I said, we're going to be looking at submissions to the problem that we looked at last week. What was the problem that we looked at? So the first part was the following. So just eat it. Create a mathematical model that a state could use to determine if it could feed its food insecure population using the wasted food generated in that state. Demonstrate how your model works for Texas. You may choose to use provided data, right? And so in the problem statement, presumably, right, they had data related to food wasted in Texas, okay? Right, but the key thing is, again, determining if a state can feed its food insecure population using the wasted food that state generates, okay? And so Julie kind of walked us through kind of a few aspects of, you know, the general problem solving, I might say, like triangle. And so what we'll do is we'll kind of summarize some of the ideas that came up and some of the discussion that happened, after which we'll go ahead and look at some of these submissions. Okay. And so just, you know, things to ponder, right? In general, what ideas did you have about this question? What approaches did you want to try? What questions did you have either about the data or the problem statement, et cetera? What assumptions were you starting to make? Okay. And so So these slides are copied almost random from last week. Right, the starting point was coming up with this initial problem statement, right? What is the actual kind of quantitative thing that we want to address and start answering? And so some of these ideas, right? Well, how much food is being wasted in Texas each year? How are we actually measuring that? One possibility is just, right, the caloric content of the food that's wasted. You might also want to split that up into different aspects like kind of the vitamins and other nutrients, so like protein that's wasted, fat that's wasted, etc. Right, the other question is, right, how much food do you actually need to feed the food insecure population? Again, you could measure that in terms of calories, and you could even split it up based on different kinds of food or whatever else. Another question is, sure, a lot of this food is wasted. How much of it can you actually save, or how much of it can't be saved? And that might be another aspect that you might be able to quantify. So another idea would be, well, measure food wasted just in terms of kind of the cost of the food. Yeah, so certainly, how you kind of the initial problem you come up with, that'll determine assumptions that you make, variables that you choose, etc. But yeah, so these were just some initial ideas from last time. Okay, but the key thing is we want something quantifiable, something that we can actually measure and associate to numbers, and then actually work with those kind of data points. Same. Okay, right, so we have maybe initial problem definition, or we have ideas for what this initial problem definition would be. Of course, we're going to make a bunch of assumptions to narrow the scope of kind of the questions that we have to answer, and just make the analysis easier in general. Okay, so some assumptions that were given. Well, maybe, right, the amount of food that's wasted in Texas, or the proportion of food that's wasted in Texas, that's on par with every other state or the national average. Okay, so there's nothing special about Texas. We just have the data for Texas, so that's going to be our case study. But presumably, the stuff that we reason about Texas, we can, easily translate to any other state. Okay, and so that would be one assumption we can make. Another assumption might be, well, there are different levels of food insecurity, and so, for each of these different kinds of levels of food insecurity, or these different communities, maybe they need a different kind or amount or level of assistance. Okay, and so maybe they need different meals per day, etc. And so part of that would be, well, if we really want to use this assumption and really talk about different levels of food insecurity, right, maybe we need some extra data to back this up and say that, yes, this is a valid assumption. This is how, food insecure populations work, etc. You can also assume, well, all food insecure people have the same dietary requirements. Okay. And so getting back to the question of, well, maybe some food is kind of savable, or some food waste, you can recover that, some other you can't. Maybe you'd say, well, meat, seafood, and dairy products that are lost or wasted in some capacity, those are irredeemable, and you can't actually, use them to feed the food insecure population. Of course, depending on how you set up your model, this assumption about, some of the stuff can't be recovered may be easier to work with. It may make the model more complex and more difficult to work with. Okay, and so that might be something that comes up, in the process of coming up with your solution and writing things out. Okay, but again, these are just kind of just a summary of what happened last time. Right, so we have some ideas of, right, a problem statement and quantifying what we're looking at. We also have some assumptions that seem relevant. Okay. The other aspect is, well, what are some variables and other parameters that we need? And so these are really getting towards, quantifying these aspects that we're interested in so that we can develop, right, quantitative model and start to, address the question of, can Texas feed its food insecure population using kind of the wasted food? Okay. And so, right, maybe some of these variables are, right, average calories per type of food, number of calories needed to feed food insecure population, percentage of food that can be saved, percentage of producers, distributors, consumers actually willing to try to save some of these things. Okay, and so all of these assumptions, right, are going back to the problem statement where you're working with the caloric content and the amount of calories. If instead you were just interested in quantifying kind of the cost of things, right, you'd have different variables, right? Maybe you'd just be looking at, right, the amount of money that's wasted per food type or something like that. Okay, so the variables and parameters that, right, you would come up with for your model aren't necessarily the same that other groups would come up with, but they're, right, they're very dependent on kind of question that you pose and just how things are set up. Okay, so all of this is a relatively brief summary. Certainly keep thinking about the problem, come up with your own ideas, approaches, etc. But what we're going to do in this session is we're going to start looking at some full kind of solution analyses. Okay, and so what that looks like is what we're going to do is we're going to start thinking about, or kind of getting in the mindset of like a triage judge or a judge, and saying, well, kind of on a first pass, does this submission, or at least the submission, the part one of the submission, does it check the boxes that we're looking for? Is it easy to find stuff? What do we like? What do we think could be improved, etc. Okay, and so previously, right, when we were looking at these kind of solutions, we focused on a bit more of the details, and we said, okay, well, this team is writing this up. How do we feel about this? What can we improve, etc. But now we're going to be looking at very much like, right, a bigger picture of, here is their entire submission for this part, just part one of this problem. How do we feel about it? Okay. Okay. And so these 6 questions, I'll keep repeating these questions. And as we're looking over these submissions, these are the questions to keep in mind. Okay. And so the first 2 are kind of getting at that triangle of math modeling, where, right, you have the initial problem kind of statement, or the question that you're interested in, the assumptions that you're making, as well as kind of any variables and parameters you're choosing. And then it also kind of gets into that next part, which is, developing a model, putting the pieces together, and starting to build a solution. Okay. And so as we're looking through each of these submissions, or at least for part 1, right, these are things to keep in mind. Can you find the assumptions? Are they justified? Are they justified well enough? Can you determine kind of what actual model they're using? Right. Is it like a linear model? Are they using any sort of regression? Are they using some kind of like SIR or differential model? Are they doing something more probabilistic? Okay, so like what kind of approach are they using? How clear is it? How long does it take you to figure out what they're talking about, et cetera? And just, is it easy to figure out what that model is? Do they talk about any sort of sensitivity analysis or model validation? Right, and so, right, sensitivity analysis was just introduced today. Okay, so that sort of error analysis, or, if you change these parameters, how does the output of the model change? Is that addressed in any capacity? Do they talk about any pros and cons of their models? Do they talk about situations where their model isn't actually applicable? Okay. And for a lot of these, maybe the most important thing is, right, what is their actual conclusion, right? Because part one is saying, can Texas or can these other states feed their food insecure population using the wasted food? Okay, that is the question that M3C is asking. Okay, and so then in each of these submissions, this should really be the main thing we're looking for. Do they actually answer the question? How easy is it to find the answer that they give, etc. And just in general, what are aspects of the submission that you liked? What are aspects that maybe could have been improved, or what are things that you would have liked to have seen in their submission? Okay, so as we're looking through each of these are the questions to keep in mind, right? 1 through 5, you could say, are more fundamental to what makes a competitive M3C submission. And 6 is getting towards, there may be some fundamental stuff that, may or may not be in there that you would have liked to have seen. But certainly, maybe formatting or ways that people structure their submissions, or maybe how teams use color to highlight good and bad or whatever. Those are the things to pick up and maybe decide, yeah, I really liked how this information or these results were presented. So in my own submission, I'm going to replicate something like that. But yeah, okay. So, right, the plan is we're going to look at a bunch of these submissions, and we're going to answer as well as we can each of these questions about them. Okay. And so as we start looking at these submissions, right, please, participate. Any observations you have, etc., feel free to post in chat, and then we can, get a sense of what everyone thinks about what we're looking at. Okay. Cool. Okay, so let's go ahead and get started then. So here's the first example. And so I'll give everyone maybe 2 or 3 minutes to read through it, take a look, right? Again, so one caveat, right? We're just looking at part 1. And so a lot of these submissions are kind of being removed from the context of a full report, okay? So, one thing to keep in mind. But in this case, this snippet right here, this was essentially the entirety of their part 1 submission, okay? So take a few minutes, read through, get a sense of what they're doing, and then in particular, answer each of these 6 questions. Feel free to post in chat whenever you have thoughts. Yeah, so. Okay, so feel free to start posting, observations, answers to these questions, right? Are their assumptions easy to find? Are the assumptions justified? Is the model easy to identify? What kind of model are they using? Do they do any sort of sensitivity analysis? Do they discuss pros and cons of their model? Right? What is their conclusion? Can Texas feed its food insecure population? Right? What are your observations about the submission for each of those questions? Okay, so I guess as answers are coming in, I can say my observations, right? So one, are their assumptions easy to find? Well, from the snippet, my gut response would be, it's not clear where assumptions are, right? As you start reading, you say, well, according to nrdc.org, 40% of food is wasted in America. So that might be implicitly an assumption they're making. Is it easy to find? Not necessarily. You say, according to austintexas.gov, the average person wastes $1,500 annually on food. Okay, so again, implicitly, they're making an assumption that the average person wastes this much, and their source is that. But again, it's not, clearly stated. Sure, it's there, but it takes a little digging. Okay, so let's see. So we have a response. So they don't really have any assumptions clearly stated or justified. I would agree. There was no sensitivity analysis, right? So part 3. Okay. It's correct. They don't really discuss pros and cons. I am unsure what kind of model they are using. And so I might say, well, they're using like a very simple, you might call this, if you want to give it a name, you might say like it's a linear type model. But, sure, there's nothing super fancy, super involved. Yeah. Let's see, pros and cons are not stated. There's implied answer. I like their organization. I dislike their lack of explanation. Sure. So this is definitely a start. Okay. There's a lot to be desired in the submission. So I can't see, so another response, I can't see how the table and total food money wasted in Texas comes into play. And that's a very good point, and exactly something I was thinking, right? And so we notice, sure, they have a table, they split food into different groups, percentage wasted per each group. And then they say the total amount of money wasted for each group. Okay, and so then they say total food money wasted in Texas, $15 million. But then in this analysis, they say, well, the average person or food secure person is where those numbers are coming from. So about like 34 or 35 billion dollars is how much food secure people are wasting. And then they say the amount predicted that is needed to fix the problem in Texas is about 22 billion. So they say, well, the difference between, right, the amount wasted and the amount that's needed is 12 billion. Okay. And so my mind might think, okay, well, right, they're wasting more than is needed to fix. And so maybe they can feed their food insecure population with what's wasted. But already that's, right, a conclusion that I'm making that I would have liked to have seen specifically stated after this. Okay. But again, right, it's not clear at all how this 15 million, if the 15 million comes into play here. is this total amount of kind of money wasted per food overall? How does this amount relate to kind of what they're computing here? Another question, right, coming back to assumptions. They say the amount predicted that is needed to fix the food problem in Texas is this number, right? Where is that number coming from? Is it also on austintexas.gov, right? So certainly, you know, this submission is a start, but there's a lot that, you know, is needed to turn this into, you know, a more competitive submission. Okay, so great responses, great thoughts. Let's move on and take a look at another one. Okay, and so Keisha will share the link to all of these samples. These are in the student share folder on Google Drive. And so each of the sample, right, there are 7 in there, I believe. We won't get through all of them, but what we'll do is we'll start kind of emulating this process, and then you know, the samples that we don't get to, you can think of as homework and kind of stuff to do on your own. Okay, cool. But again, right, process is the same. We're interested in a bunch of these questions, right? So assumptions, easy to find. Is there adequate justification? Can you figure out what model they're using? Is that easy to find? What aspects of the problem do they focus on, et cetera? But like, is it clear what the model is? Do they do any sort of sensitivity analysis or model validation? Do they discuss pros and cons of their approach? And, right, what is their conclusion? Do they actually give an answer to the question? And then finally, you know, what do you like? What are things that you'll take and, you know, emulate in your own submission? What are things that are missing that, you know, maybe take a note of, and be sure that you include kind of when you write up your submissions. Okay. So what I'll do is I'll then jump over here to these samples, and we'll go to sample 1. Okay. And so what I'll do here is go through this, go look through each of the questions and kind of take a look at the submission as a whole. And then for the next submission, I'll give you all time to, you know, work on your own, read through it, develop your own thoughts, and then we can discuss. But certainly as we're skimming through this, you know, anything that jumps out, any thoughts, ideas you have, feel free to share them in chat. Okay. And so again, caveat, this is, right, one small piece of a much larger submission, so context may be missing, etc. But, you know, this is a starting point. Okay. Those team, so just eat it. Problem restatement. For the first problem, we were tasked with creating a model. It could be used to determine whether we could divert wasted food. It needs to provide food for food insecure families. In other words, wanted to determine whether or not all food insecure families in a state could possibly be supported, provided that the wasted food was used productively. To test our model, we use Texas as an example. Sure, they restate the problem. Maybe something I would have liked to have seen here is, right, what is the model, or what is the approach that they're actually going to do? Are they going to focus on calories? Are they going to focus on kind of dollars spent or wasted? And that would be, you know, a small addition that would give me more kind of preparation to see, you know, what they do, what they actually do in this solution. Okay. Okay, and so moving on, so first question, right? Assumptions, are they easy to find? Bam, there is a section called assumptions. So yes, they are very easy to find. Are they justified? Right, reading through even the first one, right? Because a smaller region wouldn't differ greatly from the characteristics of a larger region. Proportions and distribution of food waste across different food groups in Texas are similar to that in the whole United States, right? And so that was an assumption that was made that we came up with last week as well. And it looks like they give a reference. Great. And right? So they have a few other assumptions that we won't read through, but so far assumptions look pretty solid. Okay, scroll down a little bit. They say, okay, let's develop the model. In order to address this problem, we compare whether the monetary value of food wasted in the state was greater than that of the food which food insecure families lack. Okay. So already they're saying they're focusing on monetary value and the costs of things, which is similar to what the last submission we looked at did. But in this case, here they're explicitly stating, this is the approach, these are the aspects of the problem that we're going to focus on. Okay. And so we have a comment, so kind of confused about assumption 3. If people have more money, won't they be less tight about a budget? So the assumption is people make educated purchases. They spend money proportionate to the standard nutrition requirements. Depending on how much of a food group they need, they will allocate their funds accordingly. And so, yeah, no, that's a valid question. And so, yeah, very valid question. Certainly a valid critique of their assumption. Maybe that would be something to address or discuss in your own submission. Another comment is maybe it's a simplifying assumption, so you don't have to get into the nitty gritty of how food insecure families actually spend the money, right? Are they spending it heavily towards one food group and ignoring the others? May or may not happen, but for this model, they don't want to worry about that or have to address that. So yes, they may be making a simplifying assumption. Yeah, and so maybe this is a point to take away when you're coming up with assumptions and writing things out. Think about holes in the argument or ways that other people could critique the assumptions you're making. Maybe some of those you can explicitly address and say, in reality, this may not happen, but here's why we're making this assumption. Okay, and so in that way, people can see that yes, you're aware of this and you're addressing it, versus I don't know whether or not this team is aware of this aspect. Okay, but anyways, yeah, so great question. Yeah, okay. Okay, so getting back to this, right? So developing the model, they decided to go the route of looking at the monetary value of everything. They focused on different food groups, monetary value of the food wasted. Let's see, so looking at states' cash receipts, percentage that is wasted in each food group, they can approximate in dollar value how much food is wasted in that state. So, right, say fruit. How much was purchased, or how much you're getting from these cash receipts in thousands of dollars, how much of that was wasted. And so then this is going to be their approximation for, how much money of fruit was wasted. Okay. Cool. And so then what do? Next, we calculated the minimum amount of money necessary to buy enough food for a food insecure individual, creating separate models for male and female individuals with age, A being the input. We calculated the calories he or she needs for a healthy diet. So already they're now trying to mix dollars and calories. Let's see how that goes. And so presumably these cubic fits for caloric needs, they're getting from some reference, sure. And they say, okay, for corresponding to a particular caloric intake, corresponding number of cups of each food group for a healthy diet, then estimated the mass per cup for each food group, and they give these quantities that are needed, presumably also coming from the same reference. And then they create these functions for these calorie amounts and inform us the cost of the food needed from each of the 5 food groups. And so then presumably P is going to be price. So price per calorie for fruits. This is their quadratic fit For vegetables, this is their fit, etc. Okay. Let's see. And so then they say expected value of the cost needed for food insecure individuals. First, need to model the distribution of ages for the food insecure population. Okay, so they're getting at, different age, different caloric and other needs. Assume that the distribution of ages for the poor match that of the food insecure, since poverty is directly linked with food insecurity. We use a quadratic model to create this probability that fits 3 data points. Okay, so here are the actual data points. So it looks like what they're doing is they're saying this function mu sub a is going to tell you roughly kind of the proportion of the population in poverty as a function of presumably age. Okay, and so sure, they have a reference for that. Something already that jumps out to me is, right, so here, right, they tried to fit this quadratic polynomial to their data. But if you look at the coefficients, right, so this coefficient, right, 0.000395 isn't super small. It's definitely smaller than the 0.02093. But what jumps out to me is the coefficient for x squared is, right, about 3 times 10 to the negative 6. So this coefficient is going to have roughly 6 zeros and then a 6. And so maybe in my head, I'm thinking, well, maybe you don't actually need a quadratic. Maybe, right, what the data is saying is really it's a linear fit. Okay? But that's just an observation. Does that actually matter? Probably not. It's just something that jumps out. Okay. And so then they say, okay, well, now we integrate the product of the probability for, where people are, kind of the proportion of those in poverty or food insecure, integrate that with the amount of kind of the price per calorie on average for male and female. And then this is going to give you a sense of the total amount of money needed to feed this food insecure population. Okay. And so you can think of this as, right, percentage of the population is food insecure, what it costs per calorie, how many calories? Well, the average for male and female at that specific age. And you say, well, for each age, what's that total price? So presumably this is kind of how they're setting up the model. I don't know if I have like a, I don't know, set name for this, but great. This is something about the model. Multiplying this value by the number of food insecure individuals in the state at the total value of food. Okay. So let's see. So running up the clock. Yeah, okay, so we can take a look. So decide to take into account amount of money needed or given in food grants through federal food distribution programs. Programs that specified how much financial assistance they gave to participants. We assume that this money would be used completely and spent proportionally in the 5 food groups. For programs that specified quantities of food allotted, we used appropriate conversions for each food group. Finally, we determined the money already spent by food insecure consumers. But right, even though they've already spent some money, it may not be enough to match their needs. Portion the amount that a customer with a mean income would spend. Okay, so in each of our 5 food groups, we know how much food insecure people are already spending. Subtract this value and the value of government aid from the total value of food needed to support healthy diets. And that'll tell us something about, how much is left over. Okay, and so then they say, great, with all this stuff, we can build our model, put things together, and start to get at these solutions. Okay. And so I think key here then, well, so, right, with these 4 values, we have a model that can determine whether the food wasted can completely sustain food insecure families by comparing the summation of the cost of wasted food, the money that they're getting from government support for food distribution programs, and the money already spent by middle-income consumers on an insufficient diet, to the money needed to provide food insecure families with a basic diet. If the summation is greater than the money needed to provide basic diets, then we have enough wasted food that can be distributed to food insecure families. Okay. So then they say, okay, for testing our model with Texas, compared it to other published food plans that the FDA has. They give a reference. Our model performed exceptionally well. Yeah, and so maybe one thing, that jumps out to me, maybe a little more information about this might have been helpful to see or justify. Okay, of course, if you're running out of space, may not be able to, but hey, this is, yeah, something that they maybe could have included a little more about. Okay, and so then they say, great, they validated it with stuff that's out there. Use their model to determine whether food waste in Texas could be used to provide a basic diet. Okay, so now they're getting towards conclusion. Let's see. So, okay, so let's go ahead and take a look at this chart, and this is the last page of part one. So they have food group, value of wasted food, value of food needed. And so looking at this, right, so value of wasted food, units are missing. Generally, this is dollars, or this might be thousands of dollars. So that's something that, maybe would have liked to have seen. But then over here, value of food needed, right? So in one of the earlier paragraphs, right, that's where they said, well, take the amount of money coming from government kind of support, and the amount that's already, being moved to support these initiatives, and then take the sum of all of those, that's going to be that. Okay, so they say from this analysis, we can determine from the negative values in the rightmost column that our model says that the combination of current spending and government assistance should be able to provide enough food in each group to the food insecure, except for vegetables. However, since the value of wasted vegetables is greater than that of the value of vegetables that Texan food insecure families are still needing, our model predicts that the wasted vegetables are adequate enough to make up this difference. Okay, and so one thing that jumps out to me already is, well, right, reading this table isn't super clear or easy. Right, a lot of the details for figuring out what's happening here are contained in, let's see, this paragraph up here. Okay, great, but presumably they say, sure, if you can read this the right way, our approach says yes, Texas can feed its food insecure population. Code. Okay, so this was rather kind of a quick whirlwind, right, survey of what's in the paper. In these last 2 minutes, or so in the next 2 minutes, feel free to post any other observations, anything that stands out, right? Is there any sort of sensitivity analysis? Do they discuss pros and cons? What do you like? What would you have liked to see? And then we'll take a look at another one. So what are your observations? What jumps out? What are your thoughts? Any other comments? Okay. Well, so maybe I can say, right, so one of the things I really would have liked to see is a better summary and discussion of the results and how to read this table. Maybe have some of the information closer to here. Maybe have a caption summarizing the key things. Okay. So one comment, so they did a good job talking about how they compared their data to that of the SBA, right? So there's some sort of, you might be able to call this maybe like a kind of sensitivity analysis or model verification or pro of the model, right? It matches stuff that's out there. Yeah, okay. Cool, so, great. So let's then move on and do a similar activity with sample 2, okay? And so how we're going to do this is now we're going to really just focus on these questions. Okay, so what we're going to do is we're going to focus on, say, part 1. Are there assumptions easy to find? You all will run through, look at sample 2 and say, yes, they're easy to find. They're on page whatever. And yes, they're justified, or no, they're not easy to find, etc. Okay, so first question, sample 2 in the student drive, right? Are their assumptions easy to find? Yes or no? Do they do a good job justifying them? Yes or no? What are your thoughts? Okay, so we can take a direct look. So go to the sample. Great problem statement, assumptions and justification right here. So we have a comment. So their assumptions are easy to find, but they could have backed it up with more data. And I would agree. And so sure, they say, our group decided to use data from 2015-16, and presumably they give references. We decide to go with 160 billion in wasted food. We give a reference. So maybe for me, I would have liked a little more justification and discussion about, one, are these assumptions justified, and maybe getting at also as well how they might start using these assumptions, or how these assumptions might play into kind of their development and kind of the model they're going to be doing. Okay, great. So they're easy to find. Are they justified? We could be a little better. Second question, is their model easy to identify? Or are aspects of how they're approaching this and, quantitatively, how they're answering the question, is it easy to figure out where that is in their write-up? Okay, so as you're, starting to write up responses, let's take a look. They say, well, sure, they're designing a model. So already they have a pun. This next model is kind of a big deal, like deal, so funny. But it looks like, right, so saying population of food insecurity, food insecure people is X, population of a given state is Y. So they're trying to compare total shortage of money for food insecure people per state should be less than or equal to the dollar amount of excess food. So maybe we'd say their model is a simple comparison. Is the amount wasted greater than the amount that's needed? And so this would be their model. And so then the question is, right, how are they getting these numbers? Is that justified? But sure, we can kind of find their model. We can kind of make sense of how they're using this stuff. Looks like they start analyzing it. And so they say, okay, so our group started by testing Texas to see what would come out of the model. Population in Texas, population of food insecure people. Was that? And was this number justified? Maybe they're getting this number from this justification. Maybe it's not 100% clear. Plug it in, maybe this could do a little better with organization. Is it like this inequality, evaluate stuff, is that inequality? I don't know. Maybe it could have been a little better organized. So I say this is not true. Okay. So maybe it's not hard to find the model, but maybe at least on a first pass, it's not 100% clear how they're approaching things, if it's well justified. So, sure, we can find it. We can kind of make sense of how they're trying to answer this question. Maybe organization can be a little better, so it's easier to find these pieces that we're looking for. Okay. Okay, and so kind of with that, right, is there any sort of sensitivity analysis or model validation or verification? And do they discuss pros and cons? Did anyone see anything in that realm when looking through the submission? Do they do any sort of sensitivity analysis? Okay. Well, so let's take another look, right? So, so they say, sure, they decide to see if their model would work for some other states, ran the calculations for Pennsylvania and California, model gave the same type of results. So I wouldn't necessarily say this is like any sort of sensitivity analysis, but it's using the same model and right, they're set up in different contexts. In conclusion, right, find the variables, write a rough description, figuring out what the values are. And then they say, we justified our model by explaining that this is the most preferable outcome due to current events. Maybe that wasn't clear to me. Okay. So some comments, don't see much of a discussion on their model results or sensitivity analysis, and I'd agree. Touch upon another comment, they touch upon comparing their model in the summary, but not really sensitivity analysis, and I'd agree, right? So that would be something that this submission is certainly missing, right? Some sort of sensitivity analysis, some sort of discussion of, pros and cons, okay? And the sensitivity analysis even could be, well, where are they getting these numbers from? What if, you change X by a bit, right? How big of a margin is there, say? Those are all things that could have been included and would have definitely improved this sort of discussion. So a question, if you're using a linear model, can you use the least segmented squares dynamic programming problem, minimal residual error line, to verify it somewhat? And my response would be probably. I don't know exactly what these segmented squares dynamic programming problems are. It's just not things that I've seen in my own work. But, you know, if you can get it to work, if it answers your question, and if you can describe it and then justify its use, go for it. It'll probably work. But okay, anyways. Okay, cool. And so, yeah, so hopefully this gives you a quick sense of, you know, especially for triage judges, as we're looking through these submissions and like looking through these pieces, seeing if these submissions check all the boxes. Hopefully this gives you a sense of what that process kind of looks like, as well as give you a sense on, you know, what are some common themes that are missing from submissions that when you're writing your own, you should definitely keep in mind and be sure to include. Okay. Okay, and so then there are a bunch of other samples. They're all the same questions. Okay, so feel free to, you know, take a look on your own time. And of course, for the winning solutions, you can find the link there. Be sure to take a look at those. And so that's it for this session.